in a rehearsal routine, what we do is based on taking example from the current class and store a subset of them into a buffer that is called memory. So we retain a small subset of examples into this kind of memory. After that, in later tasks, so subsequently, we combine in the current batch, in the current training batch, we combine example from the current dataset, no, we have to learn, and some example from this memory buffer. So the memory buffer, we can consider a memory buffer as a sort of dataset, small dataset containing examples from all previous classes. Okay? In a sense, it's like foolish maybe. So in a sense, so because we are circumvented, we are the problem of forgetting by using past data. Okay. But the problem becomes how to, for instance, avoid forgetting, how to exploit this kind of buffer, this the net we and remember that we can store just a few examples of clusters, no? So we have 10 examples per class in or 20 examples per class. So the buffer has a limited capacity. Okay? So what we want to do is exploit this buffer, and in order to reach the same performance we want that by training on non-tasks directly. Okay? So in this family of approaches, what we do is maintain this kind of buffer. And the most common technique and baseline is called experience replay. In experience replay, what we do is basically so given an example, no, we store example into the memory buffer, at least only so example will be stored into the memory buffer. No? So only a subset of example from the current task will be stored. This example can be chosen either randomly with the random criteria or based on, for instance, the example importance. Okay? There are several strategies. But in overall, during training, what we do is here minimizing this loss function. So I minimize the loss function by on a batch of example sampled from the current results DE. Okay, this is the current task. And then I sample a batch of example from my memory. Then I want to minimize the two loss function. Usually, we can consider this as two forward passes, two distinct forward passes, but we can also concatenate the two batches together and optimize a single loss function. Okay. So, in experience replay, what we do is maintain a fixed size memory buffer, for instance, 500 of example from past tests. So in this case, please note that we need a policy to decide which example we want to store into the memory buffer, and we need a policy to decide which example to remove from the memory buffer to make room, for example, for the contents. No? So we need entrance policy and exit policy, basically, okay, for managing that kind of this. Okay, so this is the general formulation of rehearsal based. So you can consider experience play. This is the pseudocode of experience. Let's try to read. So for each task, no, and for each example for each batch in the current data system, let's sample a new batch from the buffer, minimize the loss function on both the memory buffer and data from the current class, and then add the example from the current dataset into the buffer. Okay. So this is the general buffer. What we need here, we need, so as I told you before, we need a procedure to sample examples, and we need a procedure to store into the memory, to store example into the memory buffer, and to remove elements to make room for these examples. Okay. And so there are a lot of approaches in raster-based context learning. And basically, all these approaches provide you different ways to construct a memory buffer, different policies to regulate entrance and exit from memory buffer. And do you have any idea on how to do that? For instance, which criteria you will use to, for instance, select examples or remove example from and on how that.
You can remove, I don't know, you should maintain the more difficult or the more representative example.
How do you how do you model difficulty? How do you quantitate? How do you measure how much examples you should for a middle?
In which they obtain the words accuracy, for instance, for the previous. Or
Yes, so we could use these here, see?
mm.
But usually, yeah, if one example is from a training set, probably its accuracy will be one, no? Because we are training on that example. So, but we can do those function.
Yeah, but you also can use measure comparing picture to select more representative. If you select one picture and you compare with other picture and they have the same similarity, you can refuse the second one because it's
So, okay. For the format, you invite difficulty in the supervised sector task. So, and to do that, one possible solution is using the loss function. We could use the loss value of the given by comparing the output of the model with the ground truth distribution, and the loss function usually is a good proxy to measure the complexity of that. And this is one possible solution to prioritize which example will store in particular. Another possible solution is basically using case, no? We can, for instance, at the beginning of grade, we mentioned grade, we could clusterize, could apply history on our grade set based on using the model itself as a feature extractor. No? So we start from images and extract the corresponding activations. That what we can do is basically use images to find or find the most representative example in the data. Okay. So we take that K point and store the corresponding K images into the memory buffer. This is by just to that you know that cluster is introduced. There is also a process is called adding. Adding is another selection strategy that allows you to select example. No? And there is one paper, so there's the title of that paper, but there is a paper that makes sort of survey about all these kind of selections updated. Make an empirical survey where they review the random criteria, the handling strategy, the chemical strategy, and show their performance under different evaluation. So we could imagine we could tend to mix all these techniques basically reason in terms of importance. How much each example is important, how much that exactly is that example. Okay. We want to select the most representative example, basically. And however, usually if we state the random criteria, we have the problem of updating the memory buffer online. Okay. What I mean? It means that we in journalism we have two different philosophies, no, to update the result. One is update the memory buffer at the end of the training, no, and the other one is updating the memory buffer while training. Okay. For instance, maybe the best choice is updating the memory buffer at the end of the task, no? So after task finish, I can select a subset of example from the current task, no, and update the buffer accordingly. The problem with updating the buffer at the end of the task is that there are some scenarios in which I do not know when the task is finished. For instance, what happens if I do not have explicit knowledge about the end of one task and the start of the other. So in this case, I cannot say, okay, I stop now, update the memory buffer, and go straight. So the problem is, okay, it is reasonable to assume that we could modify and update the memory buffer at the end of one task, but the problem is that there are some scenarios which I do not know when that task finishes. Okay, so in all these scenarios, what we can do is updating the memory buffer during training. So while during each iteration. So while task progresses, I update the memory buffer, and I do not stop. I do not wait until the end of the task. In this case, what we could rely on is an algorithm called reservoir sampling. Reservoir sampling is basically an online strategy. So a strategy that can be performed one iteration after the other. That can allow us to update a memory buffer and maintain it updated randomly. Okay, so is like this. Okay, I will not go into the detail, but the algorithm is very, very fast and easy. I will not be in detail, but the idea of reservoir sampling is to provide you a strategy that allows you to put example in the memory buffer such that the content of the memory buffer is in terms of distribution similar to all the data the model has seen from the beginning of training until that moment. So the reservoir sampling is a sampling strategy in statistics that allows you to progressively sample new data, no, in a way that is compatible with the uniform distribution. So where the uniform distribution refers to basically I want a summary that is uniform from the start of the training to that moment in training. Okay? We want something that is very, very similar to a uniform distribution from the start, that goes from the first iteration to the last one. Okay? And reservoir sampling is something that guarantees this one. Okay? By using reservoir sampling, we have the guarantee that our memory buffer contains a summary that is perfectly fair with all data seen from the beginning. Okay. Otherwise, what is that? Yeah, for example, if we know the task boundaries, so if we know where when one task finish and when the other task starts, we can apply the techniques. For instance, we could apply the error strategy as I told you before. We could use graph information to select examples. For instance, in order to maximize the sample diversity, no? Usually, when you implement a cluster, you want to preserve two concepts: diversity. You want your subset to be as much as diverse as possible, no? So that it contains, it explains as much variance of the original data set, but also you want purity. So we don't want to noisy examples. No? So we want examples that are both diverse but pure. We want this kind of components. Otherwise, we will use the techniques. No? A lot of possible structures to populate and update them. Problem now is that when you perform experience play or raster based as we talked before, there is a problem related with overthinking, no? Because the memory buffer can contain only a small portion of data. So if we continue optimizing of that data, this is to overthink. Right? So what we do here, in what we can do, is to create some sort of hybrid approach between request-based method and regularization. In general, in deep learning, when we have problems overfitting, what we have to do is to employ regularization techniques that basically compensate for the lack of data. No? So we compensate the lack of data by leveraging additional training signals. This is basically the idea of regularization. This is one of the most common approach there is you can find. Again, using functional regularization. Okay. How? Basically, the idea of dark experience play is that of memorize into the memory of not only the images and not only the corresponding ground, but also areas to memorize the past model responses. So in that scarcer day, we put into the memory buffer also the notice. So the output of the print of the model before this example was inserted. Then during what we do is still based on the concept of replay. So we ask the model to perform well also on buffer data, but also we ask the model to replicate the outputs for that example. Okay, so in that experience replay, basically, the idea is similar to transfer without forgetting. So the approach we are seeing, but in this case, what we do is using directly the example of past tasks in order to perform knowledge distillation. So what we do is incorrectly the current model for given the example from giving example from the number parts, we iterate the model to replicate the same output we are recorded into the memory. So basically, we are asking a kind of consistency. So the model should output the same prediction. The current model should output the same prediction. He has given in output 1 second before its insertion into the number. Okay. And from a practical perspective, what we do is basically we store Z into the memory. Z is the output response of the model. We store Z. Then what we do is we sample from the other author a couple of given by pair, given by example, and each corresponding recorded at insertion count. Then, given the current model, we ask through the least square error, we ask the distance to be as close as possible. So the model should give the same logics he gave when that sample was inserted into the model. Okay, dark experience. It's a very time communication of experiences, right? Okay. Because we just add a new information to the memory buffer. This information in terms of memory space is very likely. We have many scalars, as many scalars as classes we are considering, but these scalars are very informative to guide the model in order to replicate the behavior or to present, maybe present is better word, to present the behavior, functional behavior he has before.
It could be similar if you have an approximation of a probability distribution of your memory buffer of the example, you can measure the divergence or the difference of the of how your probability distribution are changing when you add your you are in removing some of your data. It could be similar.
Usually, this objective function is based on comparing the logics. The logics are not the, just to be precise, are not the softmax output. So this logic does not sum to one, for instance, because these logics are the pre-activation of the software. Why we use usually pre-activation? Because in this circle, it has been reported in many papers that pre-activation of the software contains a lot of information, more secondary information than the software. Because you have just to, for instance, let's consider these are our jobs. No? So class 0 plus 1, these are the numbers. When we apply softmax, basically what we do is to push all this number to 0. So this is called squashing effect of the softmax function. So when we perform softmax, all secondary prediction, so not maximum prediction given to other classes, no maximum scores given to other classes. When we apply softmax, this term vanishes. But if we want to replicate the behavior of the model, it is more important to stick to this representation, to align the current responses to this representation. Because in this representation, we have more fine-grained information about, for instance, the relation between classes. Okay. So for this reason, we find here that, and that's not the softmax activation, but it's the press. Including the press softmax, we have a more comprehensive viewpoint of the information related to S, and especially on how the model has basically processed S. Okay. So, for instance, if we are considering a box, in this case, we know that this is the box, this is the logic for the cat, and so on. No? If we stick to that representation, we only see the activation of the box. But it is more informative, no? If we want to preserve the functional behavior, the model, to still ask the model to replicate also the logic corresponding. Okay? Because in this way we have access to more information learned by. Okay? This is the idea, the intuition behind that experience. It is called data, no? Because the name was basically due to the fact that we start from experience today, and but we want also to rely on knowledge distillation that was proposed by Ingeniería more or less 10 years ago. And Ingeniería is Seminario paper called this factor as dark knowledge. So sort of dark knowledge because we cannot, if you analyze the softmax, we do not see it because we usually just rely on the predictors, no? We just rely on the prediction with the highest probability. But if you look, no, this will you use it also often in the model compression, no? Model compression usually you guide the model using that kind of schema. And it's called dark knowledge because it is hidden by software, but it's still present in the model. So it's a backup signal we could use to replicate the behavior. So the idea of that experience to play is combining basically experience to play and knowledge to speak. And this step here, the correction, the regularization is simply functional regularization. Functional regularization is asking one model to behave as another. In this case, asking one model to be asked the current model. So the model is learning from the current task. We ask it to replicate the behavior of one past model. And the second information is that this concept is the concept that I explained to you. Okay. And we very much benchmarking this usually in continual learning where you make experiments using varying memory buffer size. So I made one experiment with 200 examples allowing buffer, another experiment with the random, etc. Just in order to see what happens with varying buffers. And what can be seen here is that if we compare experience replay and dark experience replay, we can see that with a small, very small variation, of the approach. It's just the only variation is basically that of adding one regularization there here with a small slight variation. We have a very considerable improvement in terms of perspective, especially when we have a few examples. Okay, so as you can see here with the light blue side, when we use much examples, it's not really important to regularize because we already have data to learn the function with no problem. The regularization matters when we are in a low training data regime. In a low training data regime, like for instance, when we are on 200 of example, then the gap between that experience today is very considerable with experience. Okay. Any concern? Have you understood basically the idea? Okay, so it's just that experience play is just a variation of experience play where we modify, where we we modify experience play by adding the logics. No? So the response, the class-wide prediction of the model for that example, 1 second before is insertion. It's insertion to the memory. Then we exploit these logics to supervise the model in later iteration. Okay? Using basically resort to function regulators. So I ask the model to give the same output picture it gave before. Okay. This is just providing this. Just a few more small note about that experience play plus plus. That is a sort of variant of experience play of that experience play. Sorry, plus plus stands usually plus plus stands for something that is slightly that you can obtain by slightly enhancing approach. No? And in this case, in that experience play plus plus, what we do is adding also the percentage loss on buffer that points. What does it mean? Let me see. Okay. There are no slides. Basically, in that experience play plus plus, we have also the loss function, the percentage loss function on buffer that. So we ask the model to be both to have to follow two behaviors. One to replicate the output of the previous model. The other one is to classify correctly the result using the like in standard experience play. So in a dark experience play class, the overall objective function is modified and an infer is introduced. The data there is basically minimizing the first entropy. So with you following the graph label, record the link. Okay. But it is still a slight variation that often slightly different. But the big gap here is given by functional regularization. Okay. This is the take-home message we should so if we want to preserve knowledge from previous tasks, what we can do is to basically preserve the behavior of the first of the individual. The behavior is basically can be seen both as in terms of output response or even in some words in terms of hidden activation. So what can I do also is preserving the internal activation patterns. Okay. There are also other approaches. There is a very huge literature about continual learning and, for instance, meta experience learning combines meta learning ideas from meta learning. In meta experience learning, what you want to do is to also learn from from the current task in a way that optimize the loss on the future task. No? Usually, what you are learning there are some approaches that have a sort of backward viewpoint, so minimize forgetting, and other approaches instead that are forward, so maximize the transfer to future tasks. Because if I maximum the idea behind is that since transfer, after that, future tasks will not override, will not need to override knowledge because they have the right knowledge to perform well and good. So having a sort of forward viewpoint is itself a way to prevent future forget, in a sense, no? Because we are already giving the future the right tool to learn the tasks, and in this way they will not override, they will not need to override us. I don't know if it's clear, but you can see the problem from each perspective. Avoiding risks and go see beyond. So try to see forward. Okay. Other approaches I thought, which is quite similar to what experience today, in a sense, and reality is of memory that still use memory buffers, but involves sort of quadratic programming problem, so optimization problems, in which what we want to do is to set up a constraint optimization problem in which what we ask the model, current model, is to make an update set on the current answer, but without increasing the loss on the buffer. So the model can move, can learn a new task, but through a constrained optimization problem, it has to remain in a trajectory that does not mark performance on the stage. Okay. So this guy episode of memory, and also the final remark about the literature, learning the prompt. Learning the prompt and is a basically that combines idea of prompt tuning and architectural legal, I will say. So in learning the prompt, I think it's a no. But instead of having different columns, different branch of layers, I have different prompts. So I start from pre-training that one. No? Then for each task, I learn from this set of no? Then we learn from what I do. So the advantage with respect to progressing neural network, I guess you can feel it, is that by learning prompt into the prompt, like in prompt basically, we are reducing so much the number of parameters we have to learn for each shape. No? We just need to learn in topics. But so we have a huge advantage with respect to progressive neural networks. And the other advantage is that in learning prompt, the authors propose to use a sort of key query strategy to select the prompt. Because you know that in that kind of architecture, you need to know the task identifier, no? In order to identify which column to activate. You learn the prompt, they avoid relying on task identifiers and use up query key selection strategies. Okay, so given an image, a query is processed and that's and then we select the prompt with the highest similarity to the query. Okay, so just to let you know that the techniques we have seen yesterday about parameter efficient approach can be used in computer vectors. Prompting, LoRa, stress. In this case, what we have to do is to devise a selection strategy. Which prompt, which given an image, which prompt we should use to make a forward pass at interest time. This is the problem of the linkage. Also, we have mentioned. Okay. Questions? Now, now the original program, which was in another form, I should talk you about the learning, no? But I know that many of you already have a strong background today. So even with Natalia, we decided to cover a slightly different part that may probably you do not know well, and maybe never well. It is about modern medicine, right? So maybe we passing this time to be finance to talk about learning, but I like the idea of talking to you about modern medicine. What is the idea of the person? Okay. Yes. Is it possible basically to exploit parameter definition, fine tuning, or fine tuning to multitask to reach multitask capabilities? So let's suppose I have two tasks, no? I have one fine tuning or fine tuning on task A, one model fine tuning on task C. Is it possible to merge corresponding models? Is it possible to create one model that is good for both without further retraining, without further retraining? This is the core problem of model matching. So the core problem of model matching is for instance, let's consider Hugging Face. No? Let's consider the idea that we can take two models from Hugging Face, combine their weights, and obtain a new model that is good in both tests. Model matching is exactly that. So you can have a model two, so a space of models, and you have a procedure to take these models and combine their weights. Okay? Why this is interesting? This is interesting because this operation does not cost any training iteration. So we do not need training operation from such kind of thing. You can do it. You can do it for so just having out slide maybe it's useful to see the intersection, to understand the intersection between multitasking and modeling. In that case, if I have multiple tasks, I can make one simple thing. That is, for example, let's consider the case where these are T classification tasks. No, what can I do is basically make T separate classes. I can take my email, forward it into task one, forward it into task two, or forward it into task. Okay. I can reduce the problem is that there is much computation, no? I should do here in order to do that. And also I should maintain T separate versions copies of the same model. Okay. Still in a lot of application can be here. Okay. And assembly learning instead, the idea in assembly learning basically is that of given something similar to mixed programs. No, we have T models, but while in the A figure, these T models are T vertical silos, no, that are independent of each other. In ensemble learning, these T models can communicate. For instance, we can average their prediction. We can average their activation. We can mix through their activations. We still have T different forward branches, but these T forward branches can, in a way, communicate, be in order, exchanging information. This is the idea of mixed method, basically. In model managing, what we do is take the T model, combines their limits, and add one final model. Just one model with just one single coordinates, and this model is capable of performing on +1, +2, and +3. Okay? So, in separate models, I maintain T models disjoint. In ensemble learning, I try to mixture activations in order to, for instance, enable a form of transfer learning between the models. In the model management, instead, what we aim to do is to take all these models for and forge a new model that has multitask coverage. Okay? This is just providing with okay. The simplest approach to that is basically consists in average the corresponding very easy. It's quite for all those of you that know federated averaging, it's quite similar. Okay. So in this case, what can I do is I can take, for instance, model for task one, model for task two, and take an average of the corresponding weights. This is the simplest approach to perform model energy. Okay, and there is one. Do you see any problems in doing that, for instance? Okay, so for instance, let's consider a case where alpha is 0.5. So 0.5 over 1 plus 0.5 over 2 is a simple arithmetic congruence. Do you expect this works in practice? Only for two, it's going to be difficult. Sorry? Only for 2 months it's going to be difficult. If you have multiple ones, yeah, the larger the number of models you have, for sure, the more stable it is. But it depends on how many instances each of them have been checked. Exactly. No. But let's suppose the case where these models have been trained on a set number of examples. Okay? So this is the case where the two tasks are comparable, both in terms of size and okay, which is the problem behind it. I think that the main problem would be the distance between the two weights. For example, one is in a region of lower for task one, the other is a region for lower for two, and maybe the middle point element is outside the front region. That's why, for example, in further learning, every time you merge the weights of models, they are trained in a critical element, so it's more stable, and the weights are not too far from each other. Yes, just to summarize this equation graphically. Let's call this the loss landscape for task A, no? And for instance, this is the region with the lowest loss function here. So theta 1 is here. Theta 2 is here. No? When we take the mean, we are exactly here.
Outside.
Okay, alpha 0 1 plus 1 alpha 0. Okay. So if we calculate the weights, theoretically, there are no guarantees that the loss function obtained here is good for both tasks. Okay, so the take-home message is that okay, weight interpolation is something very appealing because it's very easy. But the problem is that the two tasks, no, the two optimizations are in two different loss bases. the loss basic for class 1, the loss basic for class 2, these two basic do not speak each other. We would like to be clear. No? So an average, weight average is affiliate. No? But the problem is that if we train here these two models from scratch, usually they lie in different basis of the loss function, and we cannot interpolate them. Okay, so however,
right? When actually, when talking that maybe I don't know, network one, learn the feature of ice with filter 5 of layer 7, but the other network learn the same feature but like other filter with other layers, so kind of mix those two.
yeah, it's unique. There is one case we will do here, and we worked in a paper called the direction. It's about permuting weights. I could take, for instance, I could transform the weights of theta 1 in a way that is more aligned to the loss basis of theta 2. That is basically by permuting the weights, such that I can interpolate between the corresponding weights. So in this case, will be something like alpha permuted theta 1 plus 1 minus alpha theta 2, where the loss basis of permuted theta 1 is more aligned with the loss basis of theta 2. This is called, you can find in papers mentioned the name of Git rebasing. Git rebasing is sound familiar with Git, because like Git, we aim to rebase our model, theta 1, in order to speak the same language of theta 2, basically. Okay. Other question? Okay. But there is one thing we should consider, that is one. Usually people, when start training, do not start from scratch. No? Start from what people do is start from theta 0 plus 1 theta. That is fine tuning. No? In fine tuning, we start from a pre-trained model, theta 0, and learn, for instance, through full fine tuning, or even with the LoRa or other adaptation approaches, learn how we should modify theta 0 in order to have a full fine tuning. So, and so in this case, both the two guys here have usually are fine tuned starting from the same pretraining. Then, if this condition holds, so if the two pods have been fine tuned from the same pretraining, then people and scientists have observed that this property holds. So if two models start from the same pretraining, for instance, clip, no, pretraining clip, then we can basically add the corresponding parameters. Why? Because basically the pretraining has bias optimization in both tasks to lie in regions that are similar in terms of loss phase. So this operation in general does not work, because these models have been trained from scratch with different initial condition, different initialization. then they do not speak the same language. No? But if these two models start from the same training model, click or imagine the with base training, then we have the concept of task arithmetic. So the concept of task arithmetic is that we can perform arithmetic operation in weight space. For instance, we can interpolate between 2 points and obtain a new model, no? That has some interesting properties. For instance, here we obtain, if we start from the same training model, we have this property guaranteed in a sense. Okay, so this model interpreted here is good in both task 1 and task 2. Okay, so in this case, the take-home message is that what enables model management and task arithmetic in general is the condition of starting from the same training zone. If any start from the same training, then we can perform such kind of. Why? Because we have forced these models to remain basically the same loss region.
This original model has to be retrained, or it's enough to be the same in a station?
Has to be retrained. It's really important. There is one demonstrator that makes this experiment. It is very important. Not only that the base starting point is shared. It's important that the shared intelligence here is something meaningful. Is, for instance, click or image. Why? Because if we start from click, probably the dynamics will be much dependent on click. Okay? And this happens for both models. So the two models can still understand each other. Okay. Okay. So this is the slide I would like to show you. And this image is from a paper that is called Editing Models with Task Arithmetic. And let's try to see some example, no? So in this data here, data no, is the difference between the, can we see also as difference between the fine-tuning model, theta 1, and the original model, theta 0. No? This delta is often called, as I told you yesterday, is often called task vector. The task vector for a given task, no? You can see in that image, is the vector that starts from the pre-trained model and leads you to the fine-tuned model. It's basically the difference between me and the training. Then it has been shown in this paper that task vector support the concept of arithmetic. What does it mean? It means that if we take two tasks and add the corresponding task vector, we have a new task vector, no? That performs well both tasks. What does it mean? It means that we can perform an arithmetic operation in one space, and this operation results in additive properties between the probabilities of one model and the probabilities of the other model. Okay, and this derives from ensemble because maybe in a model example here, what we do is to make something like in model example we make an average of the corresponding node. But in this case, so alpha 0 plus alpha 1 plus 1 minus alpha 0. Okay. So plus however, you have basically that your ensemble models here in white space can be seen as theta 0, plus the sum, the weights, the mean of the corresponding task factors here. Okay? That is something very similar to that operator. So the overall conclusion here is that by summing corresponding task vector, we are doing something that is very similar to weight ensemble. Okay? And for this reason, we are through task vector, we are interpolating the corresponding points in parameter space. Okay? And this is the concept of modern merging. The concept of modern merging is to take two task vectors, two or more task vectors. Each task vector is the difference between fine-tuning and perfecting. The idea is to take multiple task vectors and find new techniques to merge them. For instance, through summation, or could be two other possible merging strategies. There is a considerable literature about that. In order to find a point that performs well on both A and B. But addition of tasks by adding the corresponding base is only one operation that we could perform in task segment. For instance, it has been observed that through task arithmetic, we can also perform learning. So what does it mean? It means that if we take this task vector, this task vector points in a region when the loss starts to decrease. If we follow this task vector, if we follow this direction, then we end up in a region when the loss for that task decreases and is decreasing. But if we start from here, and follow the opposite direction, what do you want this graph? To end up in a region with the highest loss. That means the model has unlearned that option.
This will also imply that the features of the model are synthetic, meaning that because maybe you are forgetting useful information also at doing
Yes, usually you the researcher when test this behavior monitor both the loss on the downstream task that you want to learn and both the loss on other data, so on support set. Usually you want to unlearn one concept while maintaining the others as we did before. And it has been observed that this kind of operation, in most cases, allow us to forget the task, but without certain kind of other tasks or other pieces. Okay, so because we are just manipulating the model in a direction that goes in the opposite direction to the structure. That task specifically. Okay, so task calculating. So adding all the functions from the same base model basically allows you to combine these models via addition. So addition means we can sum ways or can obtain a multitask model, but also we can perform unlearning and forgetting, selective forgetting. So if we have one task fine tune, if we have one model fine tune on that task, for instance, one model fine tune on toxic behavior. We could think to fine tune this model to have toxic behavior is false. For instance, another that finds only toxic content. That idea is that we could perform zero shot unlearning, training free unlearning by simply subtracting the corresponding task vector to the pretraining. This is the idea of task calculating by subtraction. Okay. And also there is this one. Task analysis. A is to be what C is to be. It has been shown in this paper that that task arithmetic support the concept of analysis. For instance, if I know that my task vector A is related to B, like C is related to B, I can use the relation between A, B, and C to forge the task vector for a task B. For instance, let's suppose that B, okay, task vector A is the task vector for recognizing cars in a synthetic environment. No, we are recognizing cars using, for instance, images from videos. So using synthetic ones. Let's suppose B is a fine tuning in a realistic scenario. So still detecting cars, but in a realistic environment. So A stands to B. So A is synthetic, B is realistic, but following the same object, detecting the same object, so cars. Now the idea is that if I have one synthetic data set for instance, motorbikes, no, I can exploit all these operations. So tau C plus tau B minus tau A in order to create multiply the task vector for motorbikes in realistic environment. Just I can force a new model basically to recognize motorbikes in realistic scenarios by simply exploiting the uses between tasks. So synthetic cars stand in realistic cars, like synthetic motorbikes stand to realistic cars. If I do not have the task vector of motorbikes, because maybe I do not have data to fine tune the model, I can follow the task arithmetic, I can force. Okay, this is the overall area. So we see that the basic intuition behind this work is that we can leverage multiple operations to create new models on the fly without further training. This is the gift of testing. Okay? And this in particular, this is enabled by the concept of fine tuning. So in order to have all these kind of operations and in order to have them working properly, we have just to make sure that all these models, tau A, tau B, So the corresponding class vector, the class vector, the corresponding models, we have to guarantee that all those models start from the same trajectory. For instance, clean. Okay.
Yeah, but following your example with TV and TA, in which TA is synthetic and TV is more realistic, you don't have guarantee that the difference between the realistic and the synthetic could be applicable to the task C. You can
Yeah.
maybe imagine in the example, which is the difference in the ¿cómo rueda?
Will.
In the wheel, but not with the other component, maybe.
Wow. That's the idea of transfer magnetic. You want transfer the
Yeah.
residual between synthetic car, realistic car, and synthetic car. You can transfer that residual to another.
Yeah.
This is the overall conclusion. And that we will say that maybe still need some data to fine-tune that more. But from a research perspective,
Yeah.
it's very nice for you to be area that you can forge new models, new neural networks basically on the fly, based on analysis and addition, etc.
And maybe you may later do a fine tuning with more realistic, and maybe you can,
Sorry?
maybe you later could do a fine tuning, but you are started with a better model.
We are trying to apply this idea to unwritten recognition. In unwritten recognition, you are student, and we are working on unwritten recognition. You discuss your synthetic data. For instance, you can take you can open Word and write a box synthetic unwritten document, make a screen. This is your synthetic data set. Then the problem is how to create basically the problem is the distance, no? How to transfer to a distance now. So the idea is trying to what we are doing now is trying to apply this idea to this task called animation. Now, I would expect that if you have certainly if you have a few data points for the realistic scenario multiplexes, is good to further into. But in general, this approach says that this task vector involves something meaningful.
Hmm.
Okay. And just to to reconnect with the lesson of yesterday, we did yesterday. The task vector here can be implemented with law. We can take the B multiplied by A, this is, and it is our task vector. Okay, so task arithmetic can be performed using full function, but can be also performed using all the optimization techniques we have seen yesterday. Okay, for instance, LoRa can be applied to task vector. For this case, for instance, I can include my lab give toxic responses with LoRa, and then I can take the reference lab, subtract the corresponding LoRa, toxic LoRa, and say that does no toxic behavior anymore. This is the experiments they perform in this paper. So that's how you can find. Well, now I'm giving you a slide, but you can find all the references in this. So model mapping is different from the usually we have the communication round, and we discuss, and the communication round serves to basically enforce the same law spacing between models. In modern energy, we do not have any communication round. All these models are trained disjointly, so no communication. And what we need is a definite training try to assess whether this capability or in practice. Okay. And from my experience, addition works. For getting works, there are some kind of specialized training strategies that, for instance, makes this capability better, that improves these capabilities. For instance, in this case, it's really important the concept of disentanglement. So we want each task vector to be disentangled from the others, such that if we remove that knowledge, we do not override other knowledge from other tasks. Now we are exploring the task languages. I would say that for today.
We can stop. Okay.
Okay.
Okay, thank you. Great. If anyone has questions to wrap up. Otherwise, we can, if anyone wants to join, we can go to Comedores for lunch.